So this is section 2.1. I know it says 1.1, but that's because in the new book, which I'm using to teach you, the first chapter in our book is described as a prerequisite chapter, and your chapter 2 corresponds with this book's chapter 1. So don't be confused. This is for 2.1. And in this section, we're going to talk about how we describe angles, how we use radian and degree measure, and how we use angles to model and solve real-life problems. So a quick conversation about angles. When you talk about an angle, the angle has two sides and a vertex. It has an initial side or a starting side and the terminal side where the angle ends. And when we're in standard position, the initial side is here at what we would say would be 0 along the positive side of the x-axis, and the terminal side is wherever the angle is going to end. When we're talking about unknown angles, we normally use Greek letters like alpha, beta, or theta, or capital letters A, B, and C. So if you're working on a triangle, you would use capital letters for the angles and lowercase letters for the sides. When we talk about the measurement of an angle, when we measure a positive angle, that's an angle that is traveling counterclockwise, whereas an angle that is traveling clockwise would be a negative angle. Okay, and we also will talk about coterminal angles. Coterminal angles are angles that share a terminal side. So you'll see that this positive angle, alpha, has a coterminal angle that's negative, beta, because they both share this terminal side. And equally, we have the same sort of example here. This is an angle alpha, a positive angle alpha, and then beta is an angle that is 360 degrees greater than alpha. And it is also a coterminal angle because they still share a terminal side. When we talk about, you're used to degree measure most likely, and we work a lot in trigonometry with radian measure. When you talk about radian measure, a radian is the measure of a central angle that intercepts an arc length, right? The arc length is here, that is equal in length to the radius. So this angle would be 1 radian if it creates an arc length that is the same length as the radius. And when we take a look at going around the circle, you can see I've got 1, 2, 3, 4, 5, 6, and a little bit more radians. Actually, we have 2 pi radians, so that's 6.28, so it's a little bit more than 6. When we talk about quadrants, when we're talking about radians, because this is 2 pi, all the way around the circle is 2 pi. So this location is 2 pi and it's also 0. If I go halfway around, this would be pi because it's half of 2 pi. If I go halfway to the other side, that's half of pi, which is pi over 2. And then if I go another pi over 2 past 1 pi, that would be 3 pi over 2. And these are how we label up the different axis points. And these divide us into quadrants. The quadrants, like the angles, go counterclockwise. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So now if I want to find coterminal angles, one positive and one negative for each angle, if we think about, this is 9 pi over 4. So that's really 2 1/4 pi, right? So 2 pi would be all the way around the circle. That's 2 pi. And then we're going to do a quarter. Well, this would be pi over 2, so a quarter would be right there. So right off the bat, I can see that this positive angle, pi over 4, is coterminal. So there's a positive coterminal angle. And if I were to go the opposite direction, if I take pi over 4 out of 2 pi, right? 2 pi would be 8 pi over 4, and I take one of them away and make it negative, this is 7 pi over 4, which would be an angle running in the other direction, right? So if my angle goes in this direction, that's negative because it's going clockwise, and it didn't go all the way around, it was 1/4 short of 2 pi. Okay, if we work with this angle, negative pi over 3, so this is 3 pi over 2, and this is where negative pi over 2 would be. Negative pi over 3 would be right about here. So that's negative pi over 3, this angle here. If I wanted to find a positive angle, I could go around this direction, right? And again, that's pi over 3, right? This is pi over 3, less than 2 pi. 2 pi is 6 pi over 3, so 1 less would be 5 pi over 3. And then if I want to find a negative coterminal angle, if I simply go all the way around the circle again, so if I do negative pi over 3 minus 2 pi, another 2 pi around the circle, again we said 2 pi over 3 would be, or 2 pi would be 6 pi over 3. So negative 1 minus 6, that would be negative 7 pi over 3. Okay, when we want to talk about angles, right, often what's important is to be able to find coterminal angles, and it's also often important to find complementary or supplementary angles, depending on what it is we're trying to find. So if I want to find the complement and the supplement of pi over 6, remember this measure, the measure of one quadrant, is pi over 2. And this measurement here is pi. So I want to say, what's the complement of this? Well, it would be pi over 2 minus pi over 6. Pi over 2, if I want to create common denominators, if I want to create a denominator of 6, this is 3 pi over 6 minus pi over 6. That's 2 pi over 6. Or pi over 3. So that's the complement. If I want to find the supplement, I'm going to do the same thing but with pi. So if I do 6 pi over 6 minus 1 pi over 6, that's going to be 5 pi over 6, and that's the supplement. Okay, if I want to do this one more time using a new angle, 5 pi over 6, 5 pi over 6 is here. Can I find a complement, an angle that will add up to 90? No, because this is greater already than 90 degrees, or greater than pi over 2. So there is no complement. And as we already did here, these were supplementary angles. I know that pi over 6 is the supplement. Okay, talking about converting from radians to degrees, we've got these two different formulas that allow us to convert from radians to degrees. This one will convert from degrees to radians, and this one will convert from radians to degrees, and you can really tell, I think, the easiest by noticing where pi is. So in this particular case, this is going to put pi into your equation and take out degrees. So you'll see that the radians will put pi in, take degrees out. In converting from radians to degrees, it'll put degrees in and it'll take pi back out again. Okay, and these aren't mysterious in terms of where these come from. Remember, one full trip around the circle is 360 degrees, and the corresponding measurement in radians is 2 pi. And when I simplify, I get 180 degrees over pi. And if I invert that, I get pi over 180. So in this case, we want to try to convert from degrees to radians. Remember, I'm going to take my angle. I'm going to multiply by the converter, which is going to have pi in the numerator. I want to simplify before I multiply. 60 goes into 180 3 times, so this just becomes pi over 3. In this case, if I have 320 degrees times pi over 180, 320 degrees, well, I can cancel out a 10, and then I can cancel out a 2, 16, 9, and that looks like all I can do, so this becomes 16 pi over 9. Okay, so that's converting from degrees to radians. Let's convert now from radians to degrees. If I have pi over 6, and I'm going to multiply it by 180 degrees over pi, the pi's are going to cancel. This is what I mean by it takes pi out. Right? In the previous case, it put pi in. In this case, it takes pi back out. 6 goes into 180 30 times. So this is 30 degrees. And if I have 5 pi over 3 times 180 over pi, the pi's are going to cancel. 3 goes on to 180 60 times. 5 times 60 is 300 degrees. Okay, so they're pretty easy to use. You'll know you made a mistake if you end up with pi squared or with degrees squared. When you do your conversion, you just use the wrong ratio. Okay, so invert it, do it again, you should be fine. We can calculate arc length. Remember, an angle of 1 radian, measuring 1 radian, has an arc length that's equal to the radius. I can use this formula here to find the length of an arc length. What's important is it has to be the radian measure, right? Theta has to be measured in radians. Okay, and my answer will be in radians. Okay, so I have a radius of 27 inches, and I have an angle of 160 degrees, and I'd like to find the arc length. Well, this is a problem because I need my angle to be in radians. This is in degrees, so I'm going to convert it. So I can take out 10, and I can, let's see, 8 and 9, factoring out a 2, so this becomes 8 pi over 9. And now I'm just going to take the radius times the arc length. 9 goes into 27 3 times. 3 times 8 pi is 24 pi. Okay, so that's the length of my arc length. We can also use formulas for linear and angular speeds. Right? Linear speed is, of course, this way, and angular speed would be this way. Right? And this one is a little more difficult to calculate because it's not a straight line. So linear speed is the velocity is equal to arc length divided by time. And in angular speed, it's the central angle divided by time. Okay, so if we want to go ahead and do that, the second hand of a clock is 8 centimeters long. That means that my radius is 8 centimeters. Find the linear speed of the tip of this second hand as it passes around the clock face. Well, if we go back and we take a look at linear speed, we want to know, it's going to be the arc length divided by the time. Okay, but my arc length is going to be calculated by the radius, which is 8 centimeters, times the angle. Well, if it goes all the way around, my angle will be 2 pi. So S will be equal to 8 times 2 pi, which would be 16 pi centimeters. And then I want to divide the arc length, right? My velocity will be equal to my arc length, 16 pi centimeters, divided by my time. Well, it's the second hand of the clock, so it's going to be, it depends on what I want to calculate. If I want to calculate it as centimeters per second, I would divide it by 60 seconds. And I could start simplifying this. This becomes 30, and that becomes 8. This will become 4, and that will become 15. So it'll be 4 pi over 15 centimeters per second. But equally, I could calculate it per minute, which seems a lot easier to me. 16 pi centimeters divided by 1 minute, that becomes 16 pi centimeters per minute. Okay, but what's important is that you keep track of your units of measure. It didn't tell me how it wanted me to talk about time in this problem, so I make the selection. In this case, I did it both ways. And now we're going to talk about angular speed. A circular blade on a saw rotates at 2,400 revolutions per minute. Find the angular speed in radians per minute. The blade has a radius of 4 inches. So let's go back and take a look. It's the central angle divided by time. Okay, well, I want to deal with minutes, and it goes around, it rotates around at 2,400 revolutions per minute. It goes around 2,400 times per minute. So if I want to find the angle, theta would be equal to the number of times per minute it turns around times 2 pi, which is the distance, the measurement of the angle that goes all the way around. So this becomes 4,800 pi. So if our central angle is 4,800 pi, then I want to go back and I want to take my central angle divided by time, and that's 1 minute. So since I'm going to divide it by 1, it's 4,800 pi radians per minute. And if we want to talk about linear speed, I'm going to need to find the arc length. So the arc length is going to be 4 times 4,800 pi. And I'm going to divide that by time, okay, which is also going to be per minute. So this is going to be, where it's just going to come out in inches per minute. 4 times 48, we'll have 0, 0, 32, 19,200 inches per minute. Okay, so in these we're pretty much just plugging into formulas and calculating out values. Now we also might want to find the area of a sector. So when you create an angle, it defines a pi-wedged area of a circle. It's similar to a triangle, but it's got this belly that sticks out, right? Yeah, this would be the triangle, but it's got this extra, which makes it a little difficult to calculate the area. But we have a formula. It's 1/2 times the radius squared times theta, but theta has to be measured in radians again. Okay, so if I have a sprinkler that sprays water a distance of 40 feet, so my radius is 40 feet, and rotates through an angle of 80 degrees, so theta equals 80 degrees, find the area watered by the sprinkler. Well, again, they gave it to me in degrees, which means I have to convert it to radians. So first I'm going to convert to radians, pi over 180. 9 goes into, no. So if I cut this in half and I cut that in half, I take the 10 out of each, 4 pi over 9 is the measurement of this angle in radians. And then I'm going to multiply it times 1/2 times the radius squared times my angle, 4 pi over 9. Well, 40 squared is 1600, and it's still 4 pi over 9. Half of 1600 is 800 times 4 pi over 9. And if I multiply times 4, this becomes 3200 pi over 9. Okay, I don't believe that can be simplified any further. You'll notice we're leaving pi in as a constant as opposed to making it into a decimal. That's fine. You don't need to multiply this out and come up with a decimal answer. That's it for this section. We've gone through the description of angles. We've talked about how you do measurements of angles with radians. We've talked about converting from degrees to radians. And we've used angles to model and solve some simple real-life problems.